First of all, I should thank the organizers for giving me a chance of being a part of this powder diffraction mainstream, although this is only just for a while, but I will make use of my 15 minutes of glory and will walk on the red carpet here. While preparing this lecture, whose title was a little bit strange for me, but it was actually the title Bill sent me, so I obeyed his instructions. I was thinking of the subject because for me it was too complex, and definitely I had a lot of problems to find a reasonable solution for 40 minutes. And that's why, as everything in our life, this talk is a kind of compromise. Oops. Where should I am? All right, I will do this. The basic question is where powder diffraction meets quantum chemistry, or if ever, for someone. So for me, powder diffraction meets theoretical calculation of, say, quantum chemistry or solid-state physics at 3 stages of structure analysis. First, initial model building. It was mentioned here in Kenneth's talks from several aspects, so I'm not going to add a lot of more. Second, this is what I call the structure refinement, and this is probably for me the most important part. And finally, crystal chemical analysis, which is in many structural papers omitted. I mean, the papers based on the structures from powders, because they are frequently that inaccurate that to derive any reasonable crystal chemistry is all but easy, if I wish to be polite. Because it is not possible to cover all 3 parts in details, I will mostly focus on the second. But anyhow, I will touch also the first one, and will provide one example of crystal chemical analysis in the end. I will not tell you a lot about any programs or about preparing of input files, etc., because it would take another 3 hours. I will show you later on, because I realized during the last 3-4 days there's a good habit to show at least one program. I will show you a list of programs which are available. It will be a web link, so I hope it will work. If you are interested in timing, it's another point. Those calculations mostly takes hours and days, so I'm definitely not that fast to have answer in 15 seconds or maybe in 20 seconds. And if you do something wrong, it may happen that your calculations actually ends before it starts. So, initial model building. Where can we come across a model building? This is first structural model built for future structure solution in the direct space. It was mentioned here several times, so you prepare a simple model and do energy minimization of a molecule or a fragment of a moiety to get a reasonable geometry for your future experiments with any Monte Carlo-like methods. Second applications could be, this is less frequent, for geometrical analysis of electron density maxima obtained by calculation reciprocal space. This is more the task for single crystal data than for powder. If you wish to interpret electron density obtained from experimental data, this is always a little bit tricky. So you can help yourself with something obtained theoretically, which is much easier to analyze. Actually, seen from the quantum chemistry side, the model building corresponds to optimization of the geometry of a molecular fragment. Molecule, what is molecule? This is more or less evident. The fragment, say, SiO4 tetrahedron, or say in metal-organic chemistry is fancy copper atom with 6 sticks pointing to different parts of the space. And on every stick you have got, instead of lollipop, you have got a molecule, for instance. So there are always some drawbacks. For organic molecules plus some fragments built of light inorganic atoms, what I call inorganic atoms, say aluminum, potassium, or silicon. Yes, I would stop with germanium probably. A simple molecular calculation is standardly very easy. This is so frequently, you can come across the term calculation in vacuum. It simply means that the geometry of the object is not influenced by any environment. So it goes to a minimum, which is definitely a local minimum, or if you wish, global minimum without environment. So seen from the point of view of solid state, this is a local minimum. Seen from the point of molecule, this is most probably a global minimum. So be careful. It has some consequences, because if you take such a fragment and put it to environment, I mean the structure, or the structural field, it will probably change slightly the geometry, and this is, except for the case of rigid molecules, this is highly unlikely you get back the same molecule you inserted. Hint, use this level theory because this is relatively fast and includes some correlation effects, preferably hybrid functionals. Those who are specialists know what I'm speaking about. Those who aren't, ask please a specialist, not me. So this is the hybrid, the magic for hybrid functional, which is very frequently used. Plus add some split valence basis set for the valence part of the atom, right? And you should add some diffuse and polarization functions. Even if you use atoms like oxygen, it is much better to add it. The results are then they're more accurate. If possible, avoid simple semi-empirical methods like methods belonging to that NDO family or AM1, PM, God knows what, because there is a long list of these methods. They are famous for not giving accurate geometries. And if you put to your solid state search, or solid state search, direct space search, wrong method, then we are back with the GGO rule mentioned by Bill, garbage in, garbage out. You cannot expect such a method to improve the geometry of your molecule dramatically. I mean, the structure optimization from powders. Other problem could be with heavy atoms like those mentioned before. You should keep in mind that the relativistic effects, it means that the inner core electrons are moving at the speed very close to the speed of the light, could significantly influence the behavior of the atom. And the role those effects play is definitely non-negligible, even for atoms slightly beyond the first transitional matter row. It should be tested. That's very important. There is no general rule. Try this, try that, and you see the difference. And what is more accurate should be used. A hint, again, use so-called effective core pseudopotentials, ECP, because they describe the core electrons in a proper way, and you can avoid very, very complicated basis sets. But here's the problem. If you have got heavy atoms along with light atoms, your basis set should be consistent. It means even if you use effective core pseudopotential, you should add a base to describe valence part of the atom, but the quality of the description should be consistent with the quality of the description of valence parts of light atoms. Otherwise, you can be okay, otherwise you shouldn't be surprised by the results. Going back to the second What's refinement? I wonder if it has been defined here. This is something, this is a working definition for me, that a refinement is a process which improves initial model. Improvement means increasing of accuracy of the parameters and not of the precision. Take care, those things are different, although they are many, many times confused. And unfortunately, even if we call it a refinement, this procedure probably does not know about it, because sometimes it simply leads to something which one really hesitates to call an improvement. So what is moral here is, please do not confuse physics and statistics while running any refinement, not only the structure refinement. So what are the problems powder community encounters when trying to refine the structure using just the powder data? Here's a short summary. Well, maybe someone will not like, hopefully knows, and mostly ignore, but I frequently see that this is the case. Heavy overlap has been mentioned here many, many times. This is important. Small number of accurate values of structure factors. Plus, already mentioned here, factors of real structure, preferred orientation, etc., etc., etc. And if someone supposes that application of restraints is of real help, I should stress that it leads at least to maximum to the average bond distances and angles, which could be more accurate than those without restraints. But if you are looking for some finer differences in the distances or angles, don't be disappointed when applying your restraints. And now, my point of departure is that we are looking for a remedy to the difficulty of standard powder refinement, which is lack of information extractable from a powder pattern. In a powder pattern, you have got just a certain amount of information you can extract. You can never get more than it is inside. So inequality, Heisenberg inequality, holds also here. You mostly get less than is included. So what to do with this problem? The idea is to use structure optimization by total energy minimization in a solid state. Sometimes it is called crystal energy. I wonder which term is correct, but I think that total energy is more general than the crystal, because you can optimize a big cluster simulating something amorphous. Are you in doubt? Yes, I am. But structure optimization is no double refinement in the sense of the definition I used before, as it hopefully improves accuracy of the quantities of interest while starting from the rough estimates. This is actually what is done in any refinement. Now, going back to the method, the size of the problem you can handle by a standard now, DFT methods, which are much simpler than ab initio methods, running on a pretty standard laboratory computers, is approximately 1,000 atoms per unit cell. My personal experience is, thanks to Kath, 476 atoms in a cell. The composition was carbon, hydrogen, nitrogen, and chlorine, of course. Not yet published, but don't accuse me. So if you suppose if you have 476 atoms, multiply by 3, and you obtain the number of coordinates you are optimizing in one run. This number is far beyond any powder refinement. Even a good deal of single crystal refinements would have problem with this. So when you see that this number will exceed the limit for unresistant powder refinements, I would say any diffraction, any refinement based on diffraction data, especially powder refinements which frequently fail in providing accurate results for much, much smaller number of atoms. So why to do this? The main advantage for me as a crystallographer, or future crystallographer, I don't know yet, is that the atoms are not weighted by their scattering abilities. You may object that this is not a problem for neutrons. Yes, I do agree. But neutron powder pattern is still powder pattern. Nothing more, nothing less. So you have no problem with scattering abilities, but you have a problem with overlap, etc., etc., etc. The second four is that for organic structures, or even for inorganic, if there are any, you have got direct access to accurate geometry of hydrogen bonds, which is sometimes of crucial for interpretation of your structures. Further, the shape of the molecule you created or fragment in the first step is improved slightly under the constraints imposed by the crystal field. Suppose you have got several degrees of freedom and the neighbors you hadn't while preparing the initial model. And finally, when you have got the resulting wave function, you can derive several quantities like electronic densities of states describing bonding details in your structure, vibrational densities of states which are of importance for those who are trying to interpret vibrational spectra. So those who are enthusiastic about electron density in crystals, yes, here it is. You can even calculate or estimate stress tensors, vibrational spectra, etc., etc., etc. All quantities which could be analytically derived from the total energy of the wave function are in principle available. Going back to refinement, I realized that there are two different attitudes, the coexistence of Rietveld refinement, the refinement by total energy minimization. Yes, finally I added the word yet. Maybe there will be a third, fourth, and God knows what approach. But the first gives way to Rietveld refinement and uses theoretical calculation just to refine the position of hydrogen atoms or light atoms in general. And for validation of refined structure, I would really appreciate if there's someone who could explain me the word validation in this context, because I have never understood it. Sorry, maybe in the future. So this is the first approach. And the second approach, which is mine, is that I start with the phrase, this is unlikely that Rietveld refinement with all atoms relaxed can provide sufficiently accurate structure data for the structures built from more than few atoms. If you accept these, you have no problems with energy minimization. So in the second approach, the Rietveld refinement is used just for estimation of isotropic displacement parameters or of selected profile parameters, preference orientation, etc., all which is required by crystallographic journals asking for your SIF, where you should fill this or that. I should stress at this point that like the first approach, also the second has been successfully applied to both organic, meta-organic, and inorganic compounds. In principle, this is all that is your choice. I prefer the second. There's a good deal of people here probably who would prefer the first. Okay, it's definitely up to you. All right. Running such a calculation is a little bit more difficult than a standard Rietveld refinement. What is more important, your model must be complete. No dangling bonds are allowed, sorry. Your cell should be neutral. There are some codes we could handle also charged cells. But the wave function is sometimes very strange, and the calculation is sometimes really unstable. So do prefer to have the model complete. Partial occupancies, which are typical for inorganic structures, are of course not allowed. Because from the point of quantum chemistry, the atom, either it is, say, silicon, or either it is aluminum, there is no compromise, sorry. Either 14 electrons or 13 electrons. So if you wish to model partial occupancies, you should build a supercell, having one silicon here and an aluminum here, for instance, right? For 50-50. And warning, the method, although is robust, is not a method automatically leading to a global minimum. That's a disclaimer. Now, a few examples, just really few of them. Very simple organic structure, because I'm not sufficiently clever to solve a structure, so I asked Rosanna. And Rosanna solved the structure from synchrotron data, and this is the result of the solution. You see this is a slightly distorted molecule, but resembling what chemists wish to see. So it was solved, but after the calculation, the geometry was improved, and actually we could see the differences in those two bonds, which are typical for this so-called push-pull family of compounds, where electrons are moved from and to the bonds, to anti-bonding, to bonding, etc., etc. Geometry of hydrogen atoms was also obtained, so this is the structure as it is. Oh, sorry, I'm pointing to this. You could see that there are molecules interconnected by hydrogen bonds. And now you see this is the basic constituting part of the structure. Two molecules interconnected by these hydrogen bonds. So it is quite nice to see that even with the original, with the powder data, you can have such a weak hydrogen bond, which could pose a problem even for single crystal data. You can object that you can do this with time-of-flight neutrons, yes, but you should deuterize. I wonder if maybe some of you have got money for the version of these compounds, but I don't, sorry. I prefer this is cheaper. Second is inorganic. This compound is very corrosive at the temperatures above 400. So it was measured then in platinum capillary at ID31, thanks to Michela Brunelli for collecting the data. The problem of accelerator refinement would be the number of electrons, 73 for tantalum, 19 for potassium, and only 9 for fluorine. So fancy the situation. What do you measure? Yes. This is platinum, your pattern is here. But if you get rid of platinum, you see that this ID31 is really a perfect station. But the second problem for accelerator refinement is that 50% of all cumulative intensity is here. But 50% of all cumulative intensity contains only 15 Bragg peaks. It means only 12% of all are responsible for 50% of diffracted intensity. And again, I'm pointing to the number of electrons. So the structure was refined by the energy minimization. We got this. You can see there are quite nice tantalum polyhedra, tantalum surrounded by 7 fluorine atoms. And the fit, for those who are enthusiastic about R factors, see the fit and the difference. Yes, Peter would say that there is a space for improvement, but I am quite satisfied with the structure. Yes, I agree there is space for improvement. And finally, hydrogen bonds in this compound. We were interested in the interpretation of inelastic neutron scattering spectra of this compound, but the structure was available only for room temperature data. So our approach was to collect the data at the temperature, which is quite standard for inelastic neutron scattering experiments. Thanks to Jaroslav Filinchuk, data was collected, the structure was optimized, and you can see the fit is ice here. And the structure, you see that the structure is built of polyhedra connected by various hydrogen bonds, and we use this structural model to interpret INS data. Well, for those who are still in doubts, here are the details of hydrogen bonding. This is NH4 in the surrounding of oxygen atoms. Here we have a geometry of hydrogen bonds. 2 of them are really strong, and INS spectra, you really find a split of peaks responsible for torsional motions. Well, going back to my another example, there are a few of us who remembered it. This is molecule with internal code E-rings, done many, many years ago. 2 of my co-authors are sitting here. You see, it was refined with a good deal of restraints. I'm afraid that I used more restraints than was a number of atoms. Unfortunately, by those times, there was no restraint to keep the planarity, at least with the code I used. And you see that when we run with energy minimization, it looks a little bit better. So I hope that my sins, at least this one, will be forgotten one day. Right. Something very last, done in the cooperation with Radovan. The structure solved with Fox. This is pretty inorganic. Look at the number of electrons here. So iodine, vanadium, potassium, oxygen, and finally hydrogen. The structure was solved from synchrotron data collected by Walter van Beek. And here's the building unit, vanadium. This is peroxide here, one oxygen at a longer distance. And finally, this is the sixth one from iodate. Here you can find 1, 2, 3, 4, 5. And the sixth, this is the sixth oxygen coordinating vanadium atom, and one tiny hydrogen bond from the water present in the structure. Okay, for and against. I suppose that this refinement by energy minimization provides a good alternative to standard powder refinement. Although some non-crystallographic knowledge is required. Yes, it is. That's true. Maybe discouraging for someone. But what is important? Accuracy of the resulting bond distances and angles is very comparable to those typical for single crystal neutron refinements, and in some cases, in good deal of cases also with X-ray single crystal refinements. I emphasize neutrons because they are in many times less accurate than X-rays. My big four, it works. It works especially for organic structures. For inorganic structures, the most important limit could be, say, for some substituted compounds, 1,000 atoms per cell, but I wonder if such a big structure is of interest, because you are actually then trying to find a local environment in the structure while doing, say, diffraction. I mean, in the case of variable occupancies of some atoms. Now, for those who are enthusiastic about programs, oops, sorry. Oops. It should do something, I hope. Ah, it does. So this is the page you have got pointed to it also in the written part. This is a short summary of the program like CASTEP, which is available in the UK. This one would be pretty slow for crystallography. WASP, this is what I use. This is paid. Be careful. And now Abinit is free. It's quite good. Siesta, this is a Spanish version. It uses standard basis sets, so sometimes the accuracy is not very high. But this is very fast. For those who are really in a hurry, Siesta is recommended. Oh, yes, maybe there will be some more. But Abinit is really fine. Octopus is a little bit older. Casino with Quantum, Monte Carlo, be careful. This means something else than you expect. Win2K is the most accurate program, I mean the program delivering the most accurate results, but probably the slowest. Right. I should go down. Scans, Windows, this is what I love. All right. Now, going back, like in the Hindu ceremony, take the step 3 and be my friend. So the wave function is my friend, and I can analyze it further and get several quantities like electronic and vibrational densities, the distribution, electron density, etc., etc. I will show you just one example typical for chemistry, which is based also on natural bond orbitals. NBO method simply takes your wave function and calculates localized contributions, which you know probably as Lewis structures, lone pairs, bonds, bond pairs, etc., all that alchemy in chemistry. But what you can get are quite nice results. So here you can see a molecule. Those numbers here are so-called bond orders. So you would expect chemically here a single bond, and actually the bond order is quite close to 1. You would expect triple bond here, 2.85 is quite a good estimate. Here the single bond. But if you look here, you would expect 3 single bonds. This one is Yeah, quite single, 1.016. This one is definitely not double. This is 1.3 approximately, and this one is only 0.7. It means that here some electron clouds were distributed from and to bonds. Again, the same happened here, where one would expect double bonds, but the bond order is only 1.6, so it means that the electrons from the bonds were pumped to the oxygen atom. If you wish, you can see that the bond orders around this ring, which is aromatic, are all around 1.4, which is quite a good estimate. The same holds for CH bonds here, so that this ring is pretty stable, and there's actually no surprise. This method gives you also resonance structures, which are here with plus and minus here, or this one plus and minus here, and actually your molecule is a compromise between these resonance states. What was written in italic are estimated charges. You know, atomic charges are something I prefer to avoid. This is one of the numerous ways how to estimate atomic charges. This one is consistent with the bond orders. In this context, it can be used even to calculate, say, a dipole moment or its components, if it is of any interest. So this is the 3. And maybe what I told you before is something a good deal of you don't like, because you are satisfied with your refinement and would prefer to stay with it. Yes, okay, but please don't shoot at the piano player. So I just wish to show you that that could be a good alternative. Probably this is not for everybody, but I can't discriminate. Nobody can discriminate. You can find people around you who would help you with this type of calculation. And the moral is that until you haven't got a reasonable comparison of your results from Rietveld on one side and energy minimization on the other side, you can't accuse any of these methods of doing something wrong. So the message is try and you will see. Thank you very much for your attention. It's lunchtime, isn't it?